Okay. Okay, so today we will start with another new machine learning algorithm for classification. And even though it has the name of regression in it, but this is for classification, okay? It's called logistic regression. And last time we learned linear regression. But remember, okay, linear regression is for predictor values, continuous value. And logistic regression is for classification. Just like what we learned before, perceptron and add line, okay. So logistic regression, so if you recall previously when we made a linear hypothesis, so linear hypothesis is the features, so the weight, so all features weight times the features, and it's a linear relationship. And with add line, the activation function, we use the linear combination. Okay, for linear, then let's see, like assuming, so here you have the samples. We have samples like distributed like this way. Is it, if we want to find the linear for the classification, then maybe this line can kind of like separate these two different classes. Okay, above this is one class and below this line is another class. But let's see, we may run into a problem. Okay, suppose we have some outline sample points aligned here. And if you add this one extra sample, okay, then your prediction line, that may be this line. That is this line. And if it is this line, then the samples fall within this range. Then it's going to be predicted differently from previous. Suppose it's if the points located in this region, then it's the class 1, suppose, is it? And then this is class 2. But if we add this extra sample, is it? And the line going to be, the separation line is going to be this new line. Then of these points, then it's going, previously it's class 2, is it? But now it's going to go to class 1. So it will cause the prediction change, okay? That's because of the boundary shifted. So, based on the data distribution, so this, if we continue to use a linear one, then it won't work. So here there is another hypothesis function, is if we use sigmoid function. Okay, sigmoid function. So for the sigmoid function, then it's expressed like this relationship. So it's 1/1 plus E. And generally speaking, it's like HZ 1/1 plus E minus Z. And Z, we know it's net input in this case, okay, in this case. So the hypothesis is regarding the features with certain assumpted weight, and our goal is to find the optimal weight. So then the relationship we can describe is like this kind of relationship. So this function, we call it a sigmoid function. And for sigmoid function, if we take a look, its distribution. So this is some variables, is it? And here is that function, is it regarding that variable. And then the distribution is kind of, it's not linear, okay? So it's like this kind of a trend. And it's like this trend. So when the z go to positive, larger values, it's approach to 1. Approaches to 1, is it? And when it go to the larger negative values, then it goes to approach to 0. Okay. And what this can represent, so basically this function represent what? It represent the probability of a particular sample belong to class 1. Okay, so belong to certain class. Because the value, the hypothesis, the function value, the result is between 0 to 1. Okay, 0 to 1. So it can be represented as probability of a particular sample belong to certain class. Okay, and generally, when we do the prediction, we can see like if this value is greater than 0.5, is it? Then the prediction is 1. So it belongs to class, belongs to some class, is it? And otherwise, if it's go to this trend, this direction, then it's not that class. So it's 0. So that's our prediction. Okay, the prediction. So this is called sigmoid function. So if we use sigmoid function, then we consider the probability of some sample belongs to a class. Okay, belongs to a class. And if you recall, for perceptron, it's unit step function, is it? And for add line, then it's just a linear, is it? It doesn't involve probability, and here it involves probability of a sample belongs to the class, because we kind of squash the value so that it goes to either 1 or goes to a 0, because here the purpose is for classification. Is it? So how close it's getting to certain classes. So the probability, the range is between 0 to 1. Okay, so that's regarding the sigmoid function general idea. Okay, and we can then, because it represents so this function, sigmoid function, represent probability for a sample belongs to certain class, is it? So then the probability doesn't belong to the class, then it's 1 minus the sigmoid function, is it? 1 minus. But over here, we consider all samples. So for a single sample, the likelihood is it that a sample belongs to a class is the probability times 1 minus, it doesn't. No, I got it messed up. So that is the probability of a single sample. Okay, one sample the probability belongs to a class. Okay, belongs to a class. And over here, we are going to consider all samples. All samples, is it? And all samples, so if a sample is that class 1, then the probability is 5, is it? So if you have a number of them, then it's the probability times together, is it? And if it doesn't, then it's 1 minus, is it? 1 minus. And so we need to, so this is consider all samples. So you need to multiply all of them together. Okay, multiply all of the possibility regarding all samples belongs to certain class together, also considering the possibility doesn't belong to certain class. Is it so? That's why we come with this likelihood. Okay, the likelihood relationship. And it's also then depends on the weight, because weight is unknown in this case. Okay, and because we want to find the maximum, we want to maximize the likelihood, is it? Maximize the likelihood. And then we come up with this relationship. And if we take a natural log of this likelihood relationship, then we can come up with this equation. Okay, with this equation. So this is after we take a natural log of the likelihood expression. Then if you recall in Adeline, we learned the gradient descent. And for the gradient descent to work, we need to consider cost function. Cost function. So for Adeline, then the cost function is the sum of square of error, that general, and also over those 2m. Divide the total number of the samples. And for if we use logistic regression using the sigmoid for the likelihood expressions, then we can define, and we also take the natural log, then we can define this as our cost function for this new type of classification. And so we define the cost function, and we also make it to negative, okay. And then we try to minimize. Because when we use gradient descent, the goal is also to minimize the cost, minimize cost. Okay, use minimize cost, then the gradient descent algorithm is then you take the cost and regarding each individual feature's weight, okay, take a derivative. And starting with some assumed weight. So because we can define this as our cost function, so we can still use gradient descent. Okay. And then next, let's see the idea. So the cost function, okay, so it should write as a cost function, and also it's regarding weight, okay. But anyway, this is the sigmoid. Sigmoid is it, and the cost. Then we also take the likelihood, and then we take the nature log of the likelihood. Okay, but anyway. we already, previous page, we already saw the expression, etc. And because here is for classification. So for classification, so this is target value. So target value can only be like it belongs to that class or doesn't belong to that class, is it? And here we starting with binary classification. So it is that class or not that class, is it? And because of this, if it is that class, y is 1, then that cost function will be so because some of the terms will be 0, is it? So we only left the non-zero term like this. And if y is 0, then it's similar, is it? Okay, and we have this 2 expression, then if we do the plotting, we can find the relationship, okay? And generally speaking, for log, some relationship, is it? So here is between 0 to 1, okay? Then you can draw something like this, but over here we have negative log, so you can mirror it like this, is it? So that's because over here, for that z, it's between 0 to 1, is it? That z. So between 0 to 1, so the cost, then we can see, is it? So if it is belongs to certain class, then that means it approaches to 1, the probability, is it? The probability approaches to 1, and the cost, we can see it's getting to 0, is it? Approach to 0 for cost. So that is correct, is it? So if it's prediction close to classification, then cost is 0, okay? So this is based on this expression, okay? And then based on this, if it's not that class, then it's the relationship, it's log times 1 minus, is it? Then that can be described, and if we curve it and it plot it, it can be draw something like this, okay? Then between 0 to 1, then we can see when the prediction further away, is it? Then the cost is going to grow. The cost is going to grow. So that's a predict wrong, okay? So this is theoretical, so background information. So very briefly, okay, information regarding logistic regression. And always keep in mind, even though here we say it's regression here, but this logistic regression is used for classification. So the key point here is it uses the probability. Okay, and because of probability, so it's between 0 to 1. Is it between 0 to 1? And how we like to consider the probability, is it? Is we do that squash function kind of. And it's basically that sigmoid function. It's a sigmoid function. And the sigmoid function, then we, because of the sigmoid function, and we over here use gradient descent. And the gradient descent needed to be based on cost function. And over here, the cost function is based on what? Is based on, we try to maximize the likelihood. Is it? And the likelihood is what? It's based on the probability. Is it times 1 it doesn't belong to that class. Is it the relationship? And then we also take log. So that's our cost function. Okay, that's the final cost function. Okay, so we understand the general idea about the logistic regression. And next, let's see some general idea. Okay, so logistic regression is for classification. Okay, but based on probability here. Okay, it's not definite 1 or 0. Okay, it's certain probability go to that class. And also for the classification, that for the learning algorithm, normally it depends on number of features. That later on we will also see like the noise. Okay, and whether it's linear separable or not. Okay, so that's later on with some other model we will see this concept better. And generally speaking, for the classification, is that the training the algorithm, what we do is we select the features, is it, and collect training samples. And normally that's from some CSV file, okay? And then we do the model training, is that we do training. And we also need to choose some performance metric. And so far, we just learned the accuracy. But later on, we will see there are more metrics that can measure the performance, okay? Then so far, we already learned for classification. We already learned three classification algorithm: perceptron, add-line, and logistic regression. Is it? And later on, there are more. Is it? And then which one is better? Is it? So a lot of time you may need to try with different models, and then to find which one is the best. Is it? So we need to choose some classifiers. So that's what classifies different learning algorithms, and also optimize. Okay. And later on, we will also see how do we deal with like overfitting or underfitting, those issues. Is it? So it also involves you need to tuning some parameters, the hyperparameters, okay? And then we can evaluate the performance, okay, and tuning the algorithm. So that's just the general idea for classification. And in our previous example, we also learned with sklearn, okay? It provides some models and we can directly to use. But just always keep in mind, for classification, we generally use integer labels, okay? So we don't use a string. And in our example, we already discussed, we need to split the original data into training and testing set. Okay, so that's, and for the accuracy, is that you can directly use the matrix from sklearn called accuracy score. You can also, regarding the model, it also has the accuracy score. You can go ahead to use it. And the perceptron, we already learned, and the logistic regression, okay, it's linear and also it's for binary classification, okay. But of course, it can be extended to multi-class classification. So in our example, we will also see, is it, and generally speaking, to use 1 over the rest technique, is it? So you kind of linear divide multiple times, is it? And then you find the best performance ones. And then for logistic regression, we already see it's based on the odds ratio, the probability, is it in favor of a certain event. And we already saw this sigmoid function, is it? And it's also a kind of like a squash, is it? So sometimes you may also hear it's a squash function. So, so here we consider the odds ratio, is it? So odds ratio, then this is the net input, is it? Net input. And then if we use the sigmoid, then the value gets between 0 to 1, is it? So considering the probability, okay. And the net input still the same, it's the weights. So depends on the number of features, is it? And the number of weights you're going to have from W1 to Wm, okay. And the first term, remember, this one is regarding bias, okay. Okay, and then let's do a comparison between Adeline and Logistic, okay, architecturally. So for Logistic and for the activation functions, to use a linear one, okay. And then when you do the training back and forth multiple times, there's a number of iterations like this, then we try to minimize the cost, is it? And the cost is based on that square of error, is it? And over here for the logistic regression, okay, we replace the linear with the squash one, with the squash relation. So it's the value is always between 0 to 1, is it? And then the arrow also going to feedback and update. And we use the gradient descent, is it? And we define the cost function as likelihood. And we try to maximize, is it? And because we take log, so we minimize the cost, okay? So that's logistic. So logistic, the probability, we already see the output of the sigmoid, is it? It's regarding the probability of particular sample belongs to a class, okay? So with that sigmoid function, so if the activation function value is greater than the 0.5, then we say, okay, so it belongs to that class, okay? Otherwise, it's not. And previously, we also discussed, so we try to maximize the likelihood, is it? Oh, and also over here, why we can come up with this relationship is because, so in statistics, is it must have the condition that individual sample independent of each other, okay? Otherwise, you cannot just times the probability together, okay? So you must have the independent of each other, okay? And then we try to maximize take log, that. So previously we already explained this take log. And then we can define the cost function. Then the cost function is try to minimize, is it? And we try to using gradient descent, okay? So gradient descent, then if you recall, as you assume some initialized weights. Okay, weights. And then your weight is going to be updated. So this is the update of your weights. Okay, update of the weight. And for the update of the weight is what? It depends on the learning rate. The cost function take a derivative regarding the weight. Okay, regarding, and of course it's for each one of it. Is it for each one of it? And over here, if you take a look, it's regarding all the samples. Is it regarding all samples? So this is still batched gradient descent. Okay. So you update, is it until what? Until the cost, is it? So the difference between the cost is, so the cost is approaching to zero, is it? Approaching to zero, so that's for the cost. Or like the weights, the updates of the weights is very close, is it very small, then you can consider like the converge, the algorithm. And if within, normally if it's doesn't converge quickly enough, then you can also define, so false converge with certain number. So we call it a maximum number of iterations, okay? So that it won't go like too long, is it? Okay, and because we try to minimize, is it minimize? So the relationship, then it's we can find this relationship, is it? And in this expression, then y is either 1 or 0. Is it because y is either 1 or 0? So that's how we come up with the cost function. Is it expressed as these two different expression? That's because y is either 1 or 0, okay? And it says if cost approaches 0, then that means we predict correctly. Is it? Otherwise, the cost will, if you predict wrong, then the cost will go very large, okay? So the goal is to minimize cost and predict correctly. Is it? So how are we going to consider that you minimize cost and predict correctly using gradient descent? So here is cost. Here is number of iterations. Is a number of iterations. So if the change is very small, that is getting not change a lot, is it, and also getting close to 0, then that means your prediction, the model is correct. Okay, it's not 100%, it is certain percentage correct. Okay, so that's the background information regarding logistic regression. And what next? Let's see the examples, okay, so that we can have better understanding. I need to share screen. This one. Okay, the first example, it's a continuous on our website for that notebook example. The name is chapter 03 sklearn, okay, that one. And the last class, last time when we learned, it's regarding sklearn for perceptron. Okay, and this example is using the data of that iris, okay, the flower classification, if you recall. based on like the paddle length width, saddle length and width. Is it so? There are 4 features in this case. Is it, and 3 types of flowers. So we can classify 0, 1, or 2, the 3 different type of classes. Okay, so that's a very classic example. Okay, ARIS for machine learning. And the last time we already saw the perceptron one, if you recall. Okay, yeah, over here for the perceptron, is that. And this time, let's take a look at the logistic. Okay, the logistic one. So logistic, and over here at first, go to some background information. Okay, and after we understand the theoretical background about logistic regression, then you don't need to worry about this, okay? Because in sklearn, then you just directly call the logistic regression model. You don't need to worry about sigmoid. But here we just try to see ourselves about the relationship. Okay, so as usual, we still do some plotting here. Okay, so we import the pyplot, okay, from the matplot library. And first we define the sigmoid. Okay, sigmoid is defined as this, and this we just generate some random value within certain range, and then take a look how sigmoid behaviors, okay, do the plotting. So it's just regarding z and phi z, okay. So, and over here we do the plotting, and this xv line, what it defines is, we will see there is some vertical line, okay, be placed, and over here you can set where the vertical line is going to be, and here is regarding the plotting color, okay. And also over here you also want to define some limit, okay. So because over here this is regarding the y, is that this is x, but over here this is our x, and this phi z is our y, is it? Because this represents the probability, so generally it's between 0 to 1, is it? So we don't want the plotting go beyond too much, so that's why we set the limit to negative 0.1 and 1.1, okay? And we also do the label. So this is regarding plotting, and we also place the ticks, okay. So you want to force it to have 0, 0.5, and 1.1. So that's more related with our logistic regression, okay. Because 0.5, it's kind of the transition between 2 classes, okay, between 2 classes. And for this GCA, it's used to get the current axis of the graph, okay, because then we also want to do the grade here, okay. So we also see some grade line. And then we draw this, okay. So the plotting of this sigmoid function, you can clearly see, is it in this diagram, that's when the net input values go larger, then it approaches to 0, is it? And if it goes to the negative larger value, then it's getting close to 0. And then next, if you recall, we have the cost function, that the cost function. And for the cost, because it's classification, so it belongs to that class or doesn't belong to class. So that's why over here we have this 2 cost defined. And what next is just try to show us the cost relationship. And here we also consider some input values, okay? And then we do the sigmoid regarding this range of the value. And then next, we also consider the cost, okay, the cost. And then we can plot the cost relationship. So let's see. So the cost relation, you can clearly see that if you predict correctly, that then it's getting close to zero. That otherwise it approaches to infinity. That so this is regarding the math description about the cost function. And what is the next part in this example is we define our own logistic regression using gradient descent. Okay, so this is not from sklearn. Okay, this is our own version of implementation. And because it involves logistic, involves gradient descent, so we need the learning rate. So this is a learning rate. And this is number of iterations, is it, for the gradient descent to converge. And if it go beyond that, it still doesn't, then it's just stop, okay. So that's regarding, and this random state just means that you can repeat, you can reproduce, okay. Reproduce your experiment here. And the fit is just for each iteration, is it each iteration, then you just keep updating the weights, is it? And the weights depends on the learning rate. And the arrow also over here that we defined, that we defined, and also based on the activation, okay, activation. So that's regarding the fit one, and then you can do the prediction. Do the prediction. So that's regarding the gradient descent logistic implementation. And then what next one we try to do here is for our own version. Then we just consider the binary classification, okay. Is it iris settled, okay, or the versus color one, okay, just consider this two. So that's how we use this condition, is it to filter data. So here we filter data. We are not going to use all of the data, filter just consider this belongs to class 0 and class 1. These two subclass, okay. And then we start with logistic regression, and we plug in with this filtered two class data, okay. And this plot decision region is the same function as defined in the previous discussion. And so here you just plug in the data and our logistic regression, okay, model. And here is plotting regarding the prediction. We can clearly see it's classified quite well. Okay, so that's regarding the raw implementation. And what next we are going to see? We are going to see with sklearn, okay. For sklearn, over here, we also, if you recall, this is not the raw data, okay, because you can clearly see that from the result. This is already normalized. And we do the standard for feature scaling. Okay, so the data already pre-processed, okay, pre-processed. And for the training, we can see this time it's 3 classes. Okay, so for logistic regression, and we don't need to worry, okay, if you want to use logistic regression, and also it belongs to linear model, okay. And for logistic regression, you just call the logistic regression, create the model, is it? Then you just plug in the training data, okay? And this random state we already know, so it's for reproduction. You can have the same, you can reproduce this experiment. And this C, okay, later on we will discuss. This is for, this also important concept in machine learning for performance tuning. And this technique, we call it regularization. So this coefficient C is used for regularization. Okay, later on, we will explain the concept about regularization. And here we use L2 regularization, okay. So basically, it's going to use some penalty, okay, to penalize the weight. But anyway, so let's see, we train the model, okay, and over here, we also borrow that plot decision region and then plug in the value, okay, and use our logistic regression, is it, to see how the overall result it is it, and we can see that it's also pretty good, okay. Okay, and then next, let's see, for logistic regression, then how can we know, like, the class it belongs to, is it? And because it involves the probability, is it? So when you have some new sample data, is it, or testing data, is it? So this is for testing samples. Testing samples, then you can predict. Then over here it's called predict its probability. Okay, predict its probability. And for the probability, then the result, if you take a look, it has 3. Is it for, we have 3 samples. So here we have sample 1, then sample 2. Is it a sample 3? Is it 3 different samples? And for each sample, then if you take a look, those are some small values. Is it 0 point some values? Is it? This is quite small. So quite small means the probability belongs to class 0. So this is class 1, and then this is class 2. Is it? So definitely it's not going to be this class. Is it? Then it's between these 2. Is it? Looks like this one is larger than this one. Is it? So it should be this class, class 2. Is it? Okay, and then the next one, same thing. Is it? So this definitely is not going to be. So it's between this. Well, this is, so looks like it's this class 0, is it? So over here it gives us the probability, is it? And then, and we can also do sum up, is it? So sum of the columns. So it's the summation of the probability, then definitely it should be 1, is it? Then how do you find which class it is? And if you recall, previously, we also learned this argmax, is it? Argmax, then it tells us which class. Find the largest probabilities index, is it? With it, this is column index. And with this, then we know which class it is. And similar is that you can do we can also call the predict to directly give us the class prediction. And this just, it also give us the probability, okay? And this part, basically, it's already applied the argx and give us this result, okay? Okay, so today let's just stop here about the logistic regression. So next class we will continue to discuss more about the example. So I will see you all on Wednesday. Bye.